All right, I think we're differentiable. We're not differentiable at -1, so I think we're going to have an issue there.
Lurking in the shadows.
I think that's it here, right, folks? So we can't differentiate at 3 because we have a jump discontinuity. We can't differentiate at -1 because of the corner or cusp. But everywhere else should be fine, right? At least all of the other possibilities that they've given to us, I think should be okay. Given this function, find f prime using the limit definition of the derivative. You must show your work and you must use the limit definition for
alien civilizations can't comprehend my genius. Their math would pale in comparison to my superior calculations. Who can match my brilliance? No one.
No, you must show your work. Do we really have to show our work here? Okay, we need f at x plus h minus f of x all over h. So we need f x plus h squared plus 12x plus h plus 7. And then we're going to subtract all of these terms. So we need to subtract 5x squared, subtract 12x, and subtract 7. And then divide by h. So something tells me this is going to get messier before it gets better. So we need 5. We have x squared plus 2xh plus h squared. Let's distribute 12 through. 7s I can see are going to cancel right away, so let's get rid of those. So we have minus 5x squared minus 12x all over h. Next step is to distribute this 5 through the brackets. So that'll give us 5x squared plus 10xh plus 5h squared. We can do another cancellation with these 12x's to get 0. That's going to leave us with 12h minus 5x squared. And then if we've done everything correctly, this last term that does not have an h in it will cancel as well. So now we should be able to factor out an h, so we have 10x plus 5h plus 12 over h. Now we can divide this out to get 1. And if we set h equal to 0, or let h get closer to 0, this should end up being 10x plus 12, which I think is the correct answer, right? If I take the derivative of this using the power law, or power rule, it should be 10x plus. Yeah, okay, so 10x plus 12. I am happy with that. That makes sense to me. We're not going to use the limit definition here. I think we're just going to go ahead and pluck off the answers here. We just want to take a look at how to get to the second derivative. So if I want to get to the first derivative, I'm going to keep this constant here, and then we're going to go 3x squared. And then 7x minus 4 is a line with slope 7, so we're just going to grab that slope number for our derivative. Our first derivative should be 9x squared plus 7. If I want to find the second derivative, I just take the derivative of the derivative. And sometimes the second derivative has some kind of nice characteristics that we can use to help us think about the original function.
That is simple. Imaginary numbers exist on a plane, but without a real axis, they lack a defined line. Math needs both to operate. It's all about balance.
For what values of a and b is the function differentiable at 2? Oh, this is interesting, my dudes. This is interesting. Oh, how do we do this? What does this look like? So we have a function. Let's set up the x less than 2 part. That is ax plus b. And then let's set up the x bigger than or equal to 2 part. That's going to be x squared plus x. We'll add those in as sliders. Okay, so here's what our function looks like. So it's got a linear piece down here, and it's got a quadratic piece up here. And so our goal is to kind of adjust, oh, look at that. So our goal is to kind of like adjust some of these values. Oh, okay. So we're adjusting the y-intercept and the slope of this line. Okay, so it looks like if we can get the, what is this? We probably need like 4, right? No, 4.25. 5 is too much. So somewhere around like 4.4 is what we need for continuity, but we won't be differentiable there because we have a corner. So what we're going to need to do is kind of like tilt. Oh, that's weird. So we're going to have to like tilt. Yeah, I can kind of see it visually. We have to kind of like tilt this in a particular way so that the slopes kind of connect in a really, really nice way. So like maybe like that. But even then, that looks very cornery. So I'm probably going to need like a pretty intense kind of slope. And I need to kind of match that up like this, right? And I need to make this transition smooth enough that I can take a derivative there. Okay, so I guess the first thing that we should probably do is we should probably make sure that it's continuous. And we want it to be continuous at x equals 2. So that means we need the limit as x approaches 2 from the left side to be equal to the limit as x approaches maybe 2 from the right side. For values slightly smaller than 2, we're working here. So we have our ax plus b. And for values that are slightly bigger than 2, we're going to be working with x squared plus x. Now, each of these kind of sub-functions are continuous, so I can just do direct substitution of 2 in here. So what we need is we need 2a plus b to be equal to 2 squared plus 2. So 2a plus b has to be equal to 4 plus 2, which is 6. So let's call this equation 1. Now, could we also differentiate this piece by piece? Like I could find the derivative of the top piece and the derivative of the bottom piece. And I think the idea is we need those slope numbers to be equal. So if I want this to be differentiable at 2, I better make sure those slopes are the same. So find f prime for each piece. And set slopes equal to each other. So ax plus b, the derivative of that's just going to be a, and then x squared plus x, the derivative of that should be 2x plus 1. I need these slopes to be equal.
Zeta wrong. A zero matrix is indeed the null matrix. It's defined by having all 0 elements and behaves like additive identity in matrix operations. Get your math straight.
I would consider the zero matrix and the null matrix the same. So I feel like I would agree with Shou in this particular case. So we need a to be equal to 2x plus 1, but specifically, at x is equal to 2, we have a is equal to 4 plus 1. We need actually a is equal to 5. So that's going to give us our value for a. Now we can actually sub that back into equation 1. So we know that 2 times a plus b is equal to 6. So 10 plus b is equal to 6. So b is equal to negative 4. So a is equal to 5 and b is equal to negative 4. I guess we can verify that that looks good by doing this. 5 and negative 4 is what we thought. So there it is. If we zoom out, I can kind of see the dent here. I can see the dent, but it's smooth enough. This is saying it's smooth enough that I should be able to find the derivative here. All right, so it's smooth enough there, we should be able to take a derivative. Kind of weird. Kind of weird, but I like it. Kind of weird. Kind of a cool question. I like that a lot. Okay, let's do one more limit definition because we're working with I think it's important for me to show how to do something with like a square root. Everything else was polynomials, so the square roots are a little bit weirder. So we still kind of start the same way. We'll go f at x plus h. This is going to be x plus h plus 6 under the square root. And then the next step is to build the difference quotient. So f at x plus h minus f of x over h. That's going to be x plus h plus 6 minus x plus 6 all over h of this. And then we're going to use a sneaky technique called rationalization. So we're going to multiply by this term in the numerator. We're going to change the minus sign to a plus sign in between them. And we're doing that for a very specific reason, to get difference of squares. So doing this multiplication in the numerator should give us a difference of squares. So I'm going to get x plus h plus 6 under the root squared, and then I'm going to get x plus 6 under the root squared. So that's the point of doing this kind of multiplication, is to remove these square roots. Now the denominator is going to be a little annoying because not really much we can do down here, but let's just keep it maybe in factored form, and hopefully this h over here will cancel out in the next step or two. Let's take a look at this numerator. This numerator becomes x plus h plus 6 minus x minus 6. So we're going to be able to get rid of some stuff here. And then notice that the h is going to divide out as well. So this h and this h will divide out and give me just a 1 in the numerator. And then we can consider what happens as h tends towards 0. So we're going to get 1 over, we'll get x plus 0 plus 6, which is just x plus 6 under the root, and then we'll get another copy of that. And usually what we do is we combine those two copies of root x plus 6 together. So we say we have two copies of root x plus 6, and that's going to be our f prime of x. So that's a square root using the limit definition. Maybe slightly easier, maybe slightly harder compared to polynomials, I'm not really sure. But with square roots, we're always using this kind of rationalization technique to get difference of squares. So that's a pretty common technique that we use there. All right, that should take care of 10.6.